basic molecular structures.
In this presentation, we will apply the principles of electron pair domain theory, also known as VSEPR theory, to describe the molecular geometry of basic molecules.
What are electron pair domain theory and valence shell electron pair repulsion theory? What do they say? How do we use them? Well, they basically say that negatively charged electron pairs, domains, arrange themselves as far apart from each other as possible, thereby determining the molecular structure. Now, just for your information, electron pair domain theory is the more modern name for this theory. VSEPR theory is the older one, but they are essentially the same theory. Let's start with some definitions first. ED stands for electron domain, which could be either a single, double, triple bond, a lone pair, also known as a non-bonding pair, or even a lone electron, which does exist in some structures. We also use a shorthand for describing the molecular geometry, and the shorthand is this. Letter A represents the central atom of the structure. Letter X represents the other atoms, the atoms that are attached to the central atom, and E represents a lone pair. We will now start describing the various molecular structures. We will start with the simplest one, the linear. All you have to do to understand this is imagine that you have two negatively charged electron domains on the surface of a sphere that will, of course, position themselves as far apart from each other. Therefore, they will position themselves at 180 degrees from each other. Now, in this structure, we have actually two possible molecule types. We have what we call AX2, meaning one central atom and two bonded atoms to that central atom with no lone pairs. The electron domain geometry for that we call linear. And all we show for this, we just show the letter A, right, with two electron domains placed on either side. Then, if we're asked to describe the molecular geometry, we then introduce the atoms themselves. Now, I cannot do this for this particular structure, but in this case, imagine that, let's say that A could be any atom, such as, let's say, I don't know, sulfur, just to come up with something. And the axis could be other atoms, such as, let's say, chlorine. In the molecular geometry, I do have to show the actual atoms, and I also have to indicate the angle that exists between the two electron domains. Another possibility for this type of structure is a molecule that has only two atoms, in which case we just don't even know which one to call the central atom, or maybe they're both other atoms. It doesn't really matter. The structure is linear because we have one electron domain between two atoms. And again, with the molecular geometry, we have to specify the angle and we have to show what the atoms really are that are involved in this particular molecular geometry. For example, the two A's could be, let's say, two atoms of hydrogen. Here are examples of the linear type. The beryllium chloride and carbon dioxide are of the AX2 type. Now, question, how is it that I know that these are the molecular geometries? Well, first, I had to draw the Lewis structure. There is no way that I can guess what the molecular geometry is unless I write the Lewis structure for that particular formula. And hydrogen monochloride is also a linear example, as you can see here, but of the A2 type. So let's go on to a structure that contains 3 electron domains. Adding a third electron domain to the surface of our sphere will cause the electron domains to move away from each other as much as possible, once again, and the only arrangement that can provide that distance, the maximum distance possible, is for the 3 domains to be on the equatorial plane at 120 degrees away from each other. For a 3 electron domain structure, I have 2 possible classes of molecules. The first one is AX3, in which I have the central atom bonded to 3 outer atoms, but no lone pairs. The electron domain geometry is known as trigonal planar, where I have the central atom and 3 electron domains jutting out from that central atom on a plane. The molecular geometry is also in this case known as trigonal planar, and again, whenever I show the molecular geometry, I have to show all the atoms involved and include an angle. And examples. We have, in this case, the nitrate ion, we have the carbonate ion, and we also have boron trifluoride. If you do the Lewis structures, you will see that these are the only possible molecular geometries for these molecules. The other possibility for a 3 electron domain structure is known as bent, angular, or V-shaped. This is known as the class AX2E, in which I have 2 atoms bonded to the central atom and 1 lone pair attached to that central atom. The electron domain geometry does not change because I still only have 3 electron domains around the central atom, but the molecular geometry does change. First of all, it's called bent, or angular or V-shaped, and that electron cloud actually pushes the 2 bonding pairs a bit away from each other. Therefore, the angle between the 2 bonding pairs is typically a little bit less than 120, but typically, in a regular test or web assignment, stating that the angle is 120 is acceptable. And here are 2 examples of the AX2E type, the tin 2 chloride and the sulfur dioxide. As you can see, the angle between the bonding pairs is somewhat less than 120. Let's now talk about the 4 electron domain structure. If you can imagine the 4th electron domain approaching the sphere at the North Pole, then I think you can see that the other 3 electron domains will be equally pushed away towards the South Pole until all the repulsions balance out, so that the resulting structure has really 4 corners to it, and we call that kind of structure tetrahedral. So there are 3 different types of 4 electron domain geometry. The first one is known as AX4, in which the central atom is bonded to 4 atoms. No lone pairs exist. The electron domain geometry is simply called tetrahedral, and the molecular geometry, in which you show all the atoms once again, shows that the angles between the bonding pairs are all 109.5. So here are 2 examples of the AX4 tetrahedral structure. Methane on the left, CH4, and the ammonium ion on the right. Notice that we're using projection tools, artistic tools, to indicate that this structure it's not flat, it's three-dimensional. So the way you need to read this is when you see the solid lines, as in, let's, for example, look at the left. When you see the solid lines between the carbon and the hydrogen, that means that those bonds are in the plane of the screen of the paper. The dashed line means that that bond is receding behind the face of the screen, whereas the solid triangle means that that bond is projecting out of the screen. So essentially, this is sort of like a tripod structure. I hope that's clear. If not, please ask me questions about it in the next Illuminate session. The second tetrahedral structure possible is known as AX3E. Obviously, that means 3 bonded atoms and 1 lone pair. The electron domain geometry never changes its name. It's tetrahedral. It's sort of like that's the name of the family. But the molecular geometry does take on a new name. We call this, when we have 1 lone pair, the trigonal pyramidal. And again, the lone pair pushes the other bonding pairs somewhat away from itself, making the angle between the bonding pairs a little bit less than 109.5. But once again, typically in most tests and on web assignment, if you indicate 109.5, that's probably correct. Here is 2 examples of the AX3E type, and that would be ammonia, NH3 on the top, and the hydronium ion on the bottom. The angle between the bonding pairs is somewhat less than 109.5. And by the way, for ammonia, you must know the angle. Typically, you're asked to know exactly what the angle is, which is 107.5, or 107 is also accepted typically. The third structure possible is AX2E2. Obviously, there are 2 atoms bonded to the central atom, but also there are 2 lone pairs. The electron domain geometry does not change its name because we're still dealing with 4 domains. And the molecular geometry, once again, changes its name to either bent, angular, or V-shaped. And you might ask, wait a minute, didn't we see one before that had a name just like it? Well, that was the trigonal planar bent, angular, or V-shaped. This is the tetrahedral bent, angular, or V-shaped. The 2 electron lone pairs do push away the bonding pairs even more strongly, and therefore the angle between the 2 bonding pairs ends up being less than 109.5.
The best example for this structure is water. As you can see here, the 2 non-bonding pairs are pushing away the 2 bonding pairs, the bonds that connect the hydrogens to the oxygen, and cause the angle to be less than 109.5. For water, you must know exactly what the angle is, which is 104.5. For other structures, just to state that the angle is less than 109.5 is fine.
I have included in this slide and in the next slide a summary table in which you have the various structures that are possible with 2 electron domains and 3 electron domains. What's missing here, though, is the A2 type, but I don't think that should be very hard to remember. And here is the 4 electron domain summary table. I hope these tables help you consolidate your knowledge. We have come to the end of the presentation. If you have any questions, please contact me.